Hi Year 10. Today we're looking at CC11b, ores and extraction. So do it now, task my daily task or some revision of previous topics. And I'd like to know, what do you have to do to iron ore to make iron? That's a question. What do you think you have to do? Because that's what we're finding out today. So what do you already know? Write it down. Hi there, Year 10. I'm really looking forward to seeing your thoughts on what you have to do, because you might be right, or at least partly right. What we're going to do is find out by looking at what happens to the molecules. So let's just take a look down here. Okay, and here I've got some iron ore. Okay, this is iron oxide, and it's iron and oxygen. In this case, it's iron 2 oxide because it's got 2 bonds. Okay, so this stuff, what we're going to do is we're going to heat it up. Okay, and that's not done too much. We're not breaking the bonds. But do you remember last week when we talked about a more reactive thing being able to displace? Well, we're going to put in something that's more reactive, but it's not a metal. This is really exciting. It's not a metal. We are going to put in carbon. And what happens is you've got iron here talking away to oxygen at a party, and along comes carbon and goes, "Hey, is this guy boring you? Why don't you come and talk to me? I'm from another planet." And oxygen thinks, well, with 1 degree in maths and another in astrophysics, it's either that or back to the dole queue on Monday. And so the more reactive carbon is much more attractive to the oxygen, and off it goes. This would be carbon monoxide, which, as we all know, is really dangerous. So what usually happens is the carbon will react with another iron oxide and take that oxygen as well. So there we go. We've now made carbon dioxide, and we've got iron left over. Let's write that equation down. So here's the equation for what we just did. Iron oxide and carbon makes iron and carbon dioxide. And then I've put the chemical equation underneath. FeO for iron oxide plus C will make, what does it make? I want you to write it down, then I want you to balance it. So pause the video and do it. Okay, so what does it make? It makes iron, Fe, and CO2. And I'm never going to stop saying this. I don't care what your handwriting looks like. When you do chemical symbols and formulae and equations, you make it look like you learnt it when you were 5. Okay? I'm sorry, there's just no space for pretty handwriting. In chemistry, it's got to look exact. And now we need to balance it. So we've got 2 oxygens there. So we must need 2 iron oxides, and that will give us 2 irons. Okay, here's a bit more of a challenge for you. Iron oxide can also be written Fe2O3. That's another form of iron oxide. That's iron 3 oxide. Have a go at writing and balancing that equation. So pause the video and off you go. Right, let's take a look. Iron oxide plus carbon makes iron and carbon dioxide. Okay, the first thing that we can see, we're going to ignore the ions just to start off with, because the oxygens are never going to balance out like this. We've got an odd number and an even number. So what's the first number that you can divide by 2 and divide by 3? Bang on, it's 6. So what we're going to do, so we're probably going to need 6 oxygens, because that's the common denominator, as you might say. That's the thing they've got in common. I think the denominator is going down rather than going up. So, and we've got 1, 2, 3 here, and 1, 2, oh, sorry, those are upside down, 3. Okay, so our oxygens are now balanced. Now we need to look at our ions. And I'm going to use green for iron. Fe2O3, which means we need 2 ions there and 2 ions there. That gives me a total of 4 ions. Sorry, not ions, ions. So that means I'm going to need 1, 2, 3, 4 going down here. So we think that number's going to be 4, maybe 3, maybe 2. And so what do we need for carbon? Let's see what we need for our carbon dioxide. 1, 2, 3. And so that means we are going to need 1, 2, sorry, I've run out of black, 3 there. So 3 carbon dioxides means I've needed 3 carbons. You might have been able to do that without the Lego. If you haven't, don't worry. Whatever makes sense to you. Okay, so that's how we get something like iron or any metal which is less reactive than carbon. Some metals are so unreactive, these are like platinum, gold, silver, that they don't even react with oxygen that much. And so when you're digging them up, you don't even get an ore. You are literally digging the gold nuggets straight out the ground, or digging the silver out the ground, or even, I'm sure you've heard of panning for gold, where you've got a stream and you sort of run everything from the stream through a sieve and you end up with gold nuggets in the sieve. Yeah. That's because gold, silver, platinum, so unreactive, you can literally pick it up out of the ground. In fact, the country Argentina comes from argent, which is silver in Latin and Spanish, because literally they went there and it was covered in silver. It was covered in this unreactive metal silver, and they could just pick up huge rocks made of silver. So that's where Argentina got its name. So that's what happens with unreactive metals. We don't have to react to those. They are called native metals. They are found in their native unreactive state. But what happens if you've got aluminium? Aluminium is more reactive than carbon. So if it's more reactive, we know that we're stuck. We can't react it with something that's less reactive. That won't happen. It just won't happen. So just to remind you, we'll look back at this. So reactive metal and unreactive metal. The reactive metal pushes the unreactive one out the way. Reactive metal in the compound and the unreactive metal as the metal, no, it's not going to react. Copper is not attractive or bossy enough to push the magnesium out the way. And if we look at our reactivity series here, carbon comes in just here between aluminium and zinc. So what are we going to do with aluminium? This is a bit of a tricky one because for many years nobody knew, and it was such a rare metal that Napoleon Bonaparte used to give his most esteemed guests aluminium plates to eat off, and all of the less important or less esteemed guests were given silver plates to eat off, because aluminium was so much rarer and so much more special back then. But nowadays we drink out of cans made from aluminium. We chuck aluminium hopefully in the recycling bin, not the waste bin. So how do we get aluminium if we can't react it with carbon? Well, this is where we go back to electrolysis. So let's find our electrolysis bit in the book. Here we go. So I hope you remember all of this. We've got electrolysis and we've got aluminium. We heat it all up so that it's molten, and at the cathode our aluminium ions turn into aluminium, and at the anode our oxide ions turn into oxygen. Okay, so that's how it works when we've got a more reactive metal. Unfortunately, this is really, really expensive because it costs a lot of money to generate the heat. Sorry for the break there. Didn't want you distracted by the music. So yeah, electrolysis is for all metals that are more reactive than carbon. Really, really expensive because it takes a lot of energy to heat them up to being molten. It's over 1,000 degrees C. And as well as which, we then need to pass huge currents of electricity through it. As you saw, when we did electrolysis, a couple of little batteries aren't going to cut it. You need a proper power supply to do it. And even my power supply would only work over a small distance. To do it on an industrial scale, you need loads and loads of power, loads of electricity going in there. So it's really expensive. Okay, so if you are doing standard paper, that's all you need. If you are doing the higher paper, I'm going to give you a little bit more information because you need to know about two other ways of doing it. Okay, the first one is called phyto mining. Okay, so it's mining with phyto. You may have heard that word in biology before, maybe not. Phyto is plants. Okay, and we'll do the spelling in a second. So phyto with a PH, phyto mining is plants. And what you do is you get usually brassicas, so things like cabbages. And these cabbages, you plant them on old copper mines. Okay, so copper mines are, you mine the copper out the ground until you can't mine any more out and it's uneconomical to run the mine. And so what you do then is you keep the mine and you plant cabbages on there, but you're not going to eat those cabbages. What you're going to do is the cabbages are going to soak up all of the minerals in the ground, and that includes soaking up a load of copper. And then they grow and you've got copper. Hang on a second. Okay, so there's my cabbage, and it's going to take all of the copper up through its roots, and it's going to be around the cabbage. Great. So let's chop the cabbage off and pick it up. I've now got a copper-filled cabbage. What am I going to do? I am going to set it on fire. Okay, so here's a load of fire. I'm burning it. And what you are left with, once you have burnt it, you're left with a load of ash, which is mostly carbon, and copper. You need to separate them out, and the quickest way to do that is to get some oxygen and to pass it through. So you can do that either by burning it, but you need to react it. And so along comes the oxygen. It reacts with the carbon, turns into carbon dioxide, and floats away. And you keep on doing that, and you are left with copper. So that is a fairly cheap way of getting copper out the ground when a mine is no longer viable. So that's phyto mining, and I've spelt it out here. That's plants absorbing the minerals from the soil, and then they're burnt to death to get the metal out. We can then either burn the ash again to get it out, or we can do a little bit of electrolysis to with the copper sulfate, which you will see when we're back at school, to get pure copper made. The other low-cost method of getting rid of getting metal out of a low-quality ore, okay, so these are ores that it's not economically viable to dig up, is using something called bio-leaching. And this is where you get all your low-quality ore, and you've got a nice vat of bacteria, and you tip all this ore slowly, a little bit at a time, into the vat. And the bacteria are like, ooh, soil, yum, Ew, what's that? Get rid of that. So what they do is they take all the soil and they use that to grow. They use that as their minerals, as their food. But when they get to the heavy metals, they don't like that. Too much heavy metal will kill them, which is why you've got to do it slowly. So what they do is they eat all of the soil, and their waste product, they excrete all of the metal that we want. And all we have to do is go to the bottom of the tank and sort of clear out all the metal at the bottom of it at the end of however long it takes. So if we just look in the book, I've written it down for you. So bioleaching. Bioleaching is where you feed poor quality ore to bacteria and the metal is removed as waste from those bacteria. Okay, year 10, that's it for ores and how they're extracted. Standard paper, you need to know about the displacement with carbon to make carbon dioxide. You need to know about native metals and electrolysis. Higher paper, you need to know all of that, but you also need to know about phyto mining and bioleaching. Okay, we'll take one more look in the book just so that you can pause the video and copy down anything that you want. And I will say goodbye, take care, and I will make another video for you next week all about what happens to those metals next. Take care. Bye.